My presentation has a very puzzling title, using machine learning for official statistics, from methods to statistical methods. And the reason why I chose this title like this is that I found out in the last years that there are a lot of methods which are related to statistics, but are not really statistical methods. And part of them are all the machine learning algorithms, almost all of them. And actually, all of them, when you see how some people use them and how they look at certain conditions that you have to meet for using a method. And the research started actually when I was working at Statistics Netherlands on data science, and I saw a lot of my colleagues doing very cool things with machine learning. And when I tried to replicate some of those things, I couldn't. And somehow I thought that it was something I did wrong. But at the end, I found out actually that I was doing something right. I was checking my results a lot of times, and that made it actually made me see that there is still a lot of work to do for us as statisticians in the field of machine learning. So but first, I would like to start with a subject which is related, and it is data-driven research. Where do you start with data-driven research? For me, in my opinion, everything starts at the physical world. It's actually the realm of physics where everything starts. Here is where ground truth seeds. It's not in the data. No, it's actually in the outer world where the mud is, and where the people are doing a lot of things, and that's where everything starts. And it's a data generating process which is actually making that the state of that physical world somehow visible for us. And this can be done by sensors, road sensors, weather sensors. So measuring temperature, I don't know, just think about it, how many sensors we could have around us and that we have. But also the top of your phone, the upper side of your phone is actually also a sensor. And it's actually a sensor where you can type in words at certain moments. So even there, it's a sensoric information that comes in. And so all that data that we are actually gathering are somehow sensoric data. And when we have that data, we have to transmit it. And sometimes the transmission goes wrong. Or maybe if we can pinpoint where the transmission is coming from, we can actually locate person. So that's a data transmission. Then the data has to be stored, and a lot of things can go wrong there because data storage can break. So then you lose data, but also metadata is quite important. So sometimes the metadata is not complete or something like that. At the end, when all of that is, comes together, data analysis can take place. And we have to be aware of the fact that all of this took place in front of the data analysis. So for me, that's really important. We start with the physical world, with the ground truth. We have a data generating process which transmits data, and at the end we have a data storage where we can actually do our research. And it's really important that you keep that in mind all the time when doing research like this. Actually, when you look at it, you actually see something of the total survey error getting back in here. So we start with the total survey error with the construct that has a certain validity. When you look at the operationalization, we have a measurement error, a processing error, a coverage error, sampling error, non-response error. The only thing that I miss here is that this construct is actually modeling something in reality, in the ground truth. So this should be actually somewhere at the top here, because it also refers to the target population, it refers to the construct. So yeah, for me, that physical outer world is really important. So this brings me to the subject of quality of official statistics, because we have a lot of quality dimensions where we look at relevance, accuracy, accessibility, clarity, coherence, and comparability of official statistics when you work in an official statistical office. But the thing is that all the methods that you use in those official statistics also have to meet these quality standards, because your statistics is as good as the weakest link. And when that weakest link is somehow a classification algorithm that you use somewhere in between, and that is actually making sure that the performance of your statistics is actually degrading very fast. And that is actually what I mean with that I was actually having much higher standards for my models than most data scientists around me were having at that moment. So yeah, we have to make sure that in our methods these quality standards are met. So and before I go finally to the artificial intelligence part, there's still one thing I would like to tell you about inductive research. We have a lot of discussions within our official statistics office about doing inductive research. Most of the research is deductive that you do in statistical offices, but somehow a lot of research which is done outside of statistical offices is actually inductive, starts as an inductive part. I have here the cafe, a very famous cafe wall within the world of visual perception. For a matter of fact, some people working within visual perception saw this wall and started to ask themselves, what is happening here? Why don't I see any straight lines here? Whereas actually the tiles are actually completely straight. So actually this wall is completely straight, but I don't see any straight line in here. How can that be? And then you start, as a visual scientist, you start to investigate it. I'm from my background is visual science. I worked in the field of psychophysics, and this was actually a lot of times in this way. A lot of times of our research started, and just an observation like, what is happening? What is going on here? What is happening here? And we have a lot of these: the Miller-Lyer illusion, the squintalizing grid illusion, the cafe wall illusion, of course, and of course a lot of these impossible figures, these impossible paintings. In this case of MC Escher, which asks us all the time, how can it be? How can it be that when you follow the water, everything is okay, and when you look at it globally, you see that the water is actually streaming upwards? So something is going wrong here with our visual system. And the interesting questions arise then, and then the real research starts. So in my opinion, you have the deductive and induction research, where the inductive research starts with an observation, looks for patterns, possible hypothesis, a theory, but then this theory is picked up in a deductive cycle, and you start with forming a new hypothesis, observation, and interpretation, and you come by yourself, you come in a deductive cycle, and you try to find more evidence for your theory, or you try to falsify your theory. And that's actually what I think a data scientist should do. So it is not that you start with a deductive research. It's also not that you stick to the inductive part. No, you start with an inductive piece of research where you have observational data, and you try to find patterns in there, and finally come to a normal deductive cycle, in my opinion. What I should note is that a lot of researchers stick here, just at the top here, and that is actually called abductive research, and that is actually something that we should not do. At a certain moment, the data scientist screamed at me when I was telling him that he should look at a certain external validity of his models. He started to shout at me that if it quacks like a duck and waggles like a duck, it should be a duck. And I shouted back, no, that's not true, because of the fact that you should make sure that you form a theory about it, and that you actually try to validate or falsify your theory. So then at that moment, you're working in a scientific way. So the rest of this presentation will be about machine learning and artificial intelligence. And I will start first with what artificial intelligence and machine learning is. Then I will explain something I call the asymptotical behavior towards annotated data. And I like that subject because it gives some, but I will explain it later, but it gives you some feeling about what's going wrong when doing machine learning in the field. I will say something about ground truth because ground truth is really puzzling me at this moment, and I like to discuss about it. Then the representativity of training sets, and it's actually about finding features in machine learning. And I will end with explainable AI. And but first, artificial intelligence and machine learning. Artificial intelligence is a very young field, and it tries to mimic the human behavior. That was actually the first assignment for artificial intelligence, and it was an answer to cybernetics, where people try to model behavior of animals and people by introducing feedback loops in systems and models. And artificial intelligence was an answer to that, because the cognitive science actually said that it was impossible to model human behavior like that. And that was actually in the 50s, the birth of artificial intelligence. And when you look at those first years, people were really very enthusiastic about that they would change the world in a couple of years. But when you look what we got from it after those first initial years, then we see that it was actually Claude Shannon who did something about complexity of algorithms, and the rest was all a little bit, yeah, we had a chess computer at a certain moment, but it didn't develop that fast as they thought in those first years. For a matter of fact, the original goals of artificial intelligence, by mimicking human behavior and having human intelligence present, is still not fulfilled. So we have somehow we have hit some obstacles there. But artificial intelligence also brought good things. For instance, it brought us some research on representations. How should we represent things in a computer in such a way that we can have algorithms, which are mentioned here: search algorithm, optimization algorithm, solving algorithm, and that we can let them perform on those representations. And I actually make sure that we find our way each day. If you are using a route planner to get from A to B today, then you are actually using artificial intelligence, because those search algorithms that are used, a star algorithm, actually was part of artificial intelligence. Another part of artificial intelligence, machine learning. I will zoom in on that right now. So it is about learning strategies for computers. So we try to let machines find out relationships in the data that we are collecting, in images that we have, in text that we have. And we do that in two distinct ways. One is the unsupervised learning technique, like clustering, where you just say to the algorithm, okay, I have here a set of features. So you could say these are the columns in your data set, and just try to find some relationships in this data. See if you can find clusters of data subsets in the data which belong together. And in some of the algorithms, I have to say how many of these clusters should be found, and it goes and searches for these clusters. And at the other hand, we have supervised learning, and we need to tell the algorithm what it is actually looking for. We need a variable which it has to learn. And for those, we look at classification and regression. Regression, all of the people here know that. Classification, also some people know it because of the fact that one of the most famous and easiest classification algorithm is, of course, logistic regression. But people in machine learning use that a little bit different. So we have classification and regression, which we can look at. And this presentation will be a lot about classification. So first, I try to explain classification in a different way than you normally get it explained, but it also gives you an idea what can go wrong. So what a classification algorithm does: suppose you have a logistic regression model with some features in there. So I have some columns which I use as input, as independent variables, and I have one dependent variable, my output, my target variable, the one I want to predict. Then I would like to have a model which gives a lower score to the negative items. So I have a binary classification, and it gives a lower score to the negative items and a higher score to the positive items. But the lower score and the higher score are not completely separated. And most of the times, these are not separated. Machine learners like to talk about complete separated sets, and a lot of the school book examples give you examples of how they can be separated completely. But when you are looking at images, at aerial pictures, at text, for instance, Twitter messages, or something like that, then you will find that these two sets can never be separated completely. So you always have a certain overlap between the two of them. And you have to find a certain optimal threshold where you separate them correctly. So for instance, when you put the threshold here, then you see that from this side on, all the scores will be seen as positive, and all these scores at the left side will be seen as negative. There are actually some mistakes in there, classification errors. These ones, so the red one in the right side, these are false positives. So items that are classified as positive, whereas they are actually negative. And here in this part, we have false negatives. So items which are actually positive, but are classified as negative by the algorithm. So this is because of the fact that the signal is quite noisy, and we cannot classify correctly. Now it depends on the task that you have. For statisticians, this would actually be a very good place, because in this case, the false negatives and the false positives cancel each other, which means that you have a nice indicator of the number of positives and the number of negatives. So that's actually a very nice place to start. Which can also say, well, it is for me very important that the positive cases I get are really positive, which means that I get a high precision and a low recall. And how I do that is by just moving the criterion up. Now you see that I almost have no false positives left, but I have a lot of false negatives. So this is the case where I have a high precision and a low recall. Can turn it around, and I have a low precision and a high recall. Now, in this case, I know for sure that every positive item is actually, or almost every positive item is actually in my data set here, in my positive classified set. But there are also a lot of negatives in here. So when you have a car alarm, this a very expensive car, and you have a car alarm built in, then this is actually the thing you want to have. You would like to get up in the middle of the night to see if your Ferrari is still in front of the door. Not that I have a Ferrari, but you never know. So okay, to get a little bit of feeling about how this process of classification can go wrong purely based on bias, I have a small thought experiment. And the thought experiment goes like this. Suppose I have 99 red marbles over here, and I have one green marble, and I'm blindfolded, and I have to pick out one marble. I have to predict the color correctly in 99% of the cases. The question now is, which model can predict this? And I can do this as an open question, but I don't think I have that much time left to have it as an open question. The correct answer should actually be a model that always predicts that the marble is red. But suppose I throw in 100 and how many do I have? 98 green marbles now, which means that I have 50% green marbles and 50% red marbles. And the model actually deteriorates to 50% correct prediction. So the model didn't learn anything. And you can see this very well in this model. It's a Bayesian ideal observer model, comes from psychology, was first developed in visual sciences and was picked up by social scientists. And it's actually a Bayesian view on a classifier. So I adapted it to have it as a Bayesian view on a classifier. For me, as a Bayesian, what a classifier does is that it tries to calculate the probability of a element belonging to class C, given the feature vector X, which is equal to the probability of the feature vector X, of a certain feature vector X, given the class, times the probability on that class, divided by the probability distribution of the feature vectors. And when you think about it, what happens with the red and green marble experiment is that actually this distribution was homogeneous. So there was no information in this one. So the only thing the model actually could do, and the model that we created in our mind altogether, was purely based. Was purely based on this prior condition. And even if I have some knowledge in here which separates the positives from the negatives, so these are the probability distribution in our case of the positive items and the probability distribution of the negative items. So when there is some information in there which separates them, then still this one is going to change that probability to get the probability of a class given the feature factor. And so the prior actually introduces a bias into our system, and we have to deal with that in a certain way. And the way I dealt with it is by, and one of the researches I did is by actually calculating the likelihood, you could say, actually, for a certain feature vector X, given all these prior prior probabilities, and in that way actually estimating the prior probability. So what I'm actually saying is that all classifiers have a certain problem, and that is that when you look at them as a sort of Bayesian machine which gives you back a probability, and most of them give you back a probability, or try to give you back a probability, then they actually have the probability that there is a positive item in your data set. It's actually assumed to be a value, and it's actually assumed to be the value of the proportion positives in your data set when you have a binary classifier. And you can see this here at the left panel. I created 3 data sets. One data set, actually I created a lot of data sets, but okay. The first part subset had a probability, had a proportion positives of 25%, that's the blue line. One had a proportion positives of 50%, it's the orange line, and one had a proportion positives of 75%, which is actually the green line. And what you see here is when I create test sets with a ranging with proportions positive ranging from 0.1 to 0.9, and you see that they should actually look like this, like here when I did my maximum likelihood estimate on the data set, which I explained a little bit earlier. But it actually doesn't. It actually has a big bias in there. So when I train with 25% correct, then you see that in the test set, it has a strong bias to that 25%. It's actually underestimating the proportion positives in your data set. So, and for the green, it's actually underestimating the proportion positives in your data set. And you see a lot of machine learners say you should train at 50-50, so 50% positive, 50% negative. It's actually because of that, the fact that then the errors are actually smaller. So the bias is actually smaller. But still, we have that bias in there, and it's actually not good, especially not if you want to use it for estimating, for instance, the proportion, I don't know, AI companies in the Netherlands or something like that. It has this proportion positives, which were in the training set. It already has it intrinsically in the data set already, and you need to correct for that. So we have now an algorithm which can do that. So which tries to find the proportion positives in the data set, and that's okay. Yeah. And I already mentioned it a little bit. There is a difference between classification and quantification. So within machine learning, you often threshold, or you use an arc max and maximum value. Within deep learning, so when you are using neural networks, they often apply a softmax at the end. But all of these techniques have a problem, and that it is that you remove all the uncertainty in your data. Somehow people won't be able to see the uncertainty in your data anymore. So this is actually not good. It doesn't help us that much. Suppose we would actually use a threshold for classifying companies into an ACE classification or something like that, or classify people to a certain variable. Then actually the thresholding throws away information about the uncertainty. We are misclassifying people or company at that moment, and actually this misclassification is actually appearing again in our end result. So somehow we have to deal with that. One way to deal with it is actually use the probabilities when they are real probabilities, like in my ideal observer model. Use those probabilities and adding them up so that I get an expected value. So that's actually the point. I have to see how long I'm busy. Yeah. Okay. Now I need a sip. So another point that we have to investigate how to deal with it within machine learning is what I call the asymptotical behavior towards annotated data. And this all has to do with something I already mentioned before, those visual illusions. There are two types of bias which can be introduced when using a human annotating data. And within machine learning, a lot of times humans are annotating data. And one of them is what we call a perception bias, and the other one is a perceptual bias. The perceptual bias is what I demonstrate here. As a visual perception person, I like to show them. So we have, again, the cafe wall illusion, and we have the size illusion, and we have here two tables which are actually exactly the same size, but which are perceived as a different size. And some funny things where you see an Eskimo or a face or a duck and a rabbit. So people have already a visual system which puts in a lot of bias, because we also have a prior that ideal observer model that I presented also holds for us as human observers. And we use our previous knowledge about the environment, about the size of buildings next to a person, for instance. We use that information to interpret the world around us. And furthermore, you also have your perception bias, where it is actually your culture, your norms and values, which are actually influencing the things, how you classify it. So when you are going to use a human person to actually create an annotated data set, you are taking all that ballast, all that knowledge that he built up about the world around him, all the things he assumes or she assumes about the world around him or her. You bring in all that knowledge and all that bias into the annotation, and I have a problem with that, because the question now is, to what extent is the observed ground truth, the one that is observed by that annotator, and how far is it real? And I don't know the answer, because of the fact that we have so much bias in our annotations, in the way we look at the world, that we actually cannot say that the answer we are giving is true. We cannot never be certain about that. So, and that's actually one of the problems with machine learning, because of the fact that we are very often using human annotated data. We never can get to the point where the machine learning algorithm outperforms the annotator in this way. We have to find other ways to find training data for our machine learning algorithms. So, because it's even getting worse. These mistakes in annotation, normally we split the set in a training set and test set, and sometimes in a validation set, to actually test if our algorithm is doing what it should do. But all of these training sets come from the same annotations, and they are completely different. They have exactly the same mistakes, and this is actually disturbing the way we look at the world and how we are training the models. So this is actually a big problem. How can we detect errors when they are on all the sets that we have? We can only check the internal validity of our model, because we are testing the data with actually the same annotated data as we are actually training it. There are different parts of the data set, of course, but still they are annotated in the same way. So the same mistakes are showing up in all that data. So how can we detect these errors? And if we cannot detect them, what can we say about the performance of the algorithm? I also mentioned already a couple of times the ground truth, and this is actually a discussion which is puzzling me at this moment a lot, and where I also have I'm communicating with Pim Hazelager, my old professor in philosophy of cognitive science. He's now a professor in AI and ethics, and for me, the ground truth is actually a big problem. A lot of people, I also found statisticians who think that the data you have, so the data which comes out of questionnaires or maybe registered data, is describing the ground truth. But it's actually an underdetermination problem, because of the fact that all that data is just one view on the reality. It's just one perceived view. Like I said in the beginning, all data starts with a data generating process, which is all based on sensoric data. And it's just one mapping of that reality, of that high dimensional reality on a lower dimensional data set. And somehow we have to deal with that underdetermination problem. So in my opinion, most things cannot be measured directly. And I had a discussion about this a couple of days ago, and I asked my colleagues, what can be what do you think can be measured directly? And actually, they should have answered length, because you can measure it directly, because of the fact that you can just have lines for each inch you are measuring. You can have a line somewhere on a ruler, and you just count the number of lines. So as long as something is countable, you can measure it directly. But most things cannot be measured directly. And they actually gave as an example which could be measured directly, weight, but it's actually measured by using a spring and converting the weight into a length measure. So it's not measured directly. So a lot of things cannot be measured directly. And this is actually a problem which puzzles me a lot because of the fact that everything we do within statistics is just this trying to say something about the ground truth based on measurements which are most of the time indirect. So we cannot say anything we cannot say that much about it. Yeah, I'm trying to find some grip on that problem, and to deal with it in a more general way, where you assume that there is a ground truth. Well, I assume that there is a ground truth. Does a ground truth exist for a certain question? For instance, when you look at inflation, is there a ground truth about inflation? Well, there is, because we have a currency, and we have that currency. We pay with it. We pay with you pay with pounds, and these pounds, you get something back for it, and the less you get back for it on food and stuff like that, you actually measure the inflation. The next thing is there a procedure to find it? Well, I already mentioned how you can find a procedure where you can find the ground truth in this case, the inflation, just by performing what I did. Then you know the price, you do it in another time again, and you have you know how much or less you get for your money. So and then the third question that Pim actually came with is this procedure applicable? Can we actually measure it? Is there a way we measure it? And sometimes it is hard to answer these questions. So especially the last question is quite hard. The question before is maybe a little bit simpler. And does the GT exist? The ground truth exists is even more simple. But yeah, sometimes we really have to ask ourselves if that ground truth exists, and because it's not that obvious as we sometimes assume. So, and especially when you're working with in this datafied environment of data science, you really have to realize yourself, what are you measuring? What is it that you are measuring in the real world? So and I think this is really an area of research where a lot of work still has to be done, at one side by philosophers, but also by us as statisticians. What can we say about the ground truth, and how can we try to investigate that ground truth as good as possible? So then my last point is on representativity of training sets, and then I finish, as I can see, within 40 minutes. And actually, representativity of training sets is something about the right features. And I already saw a lot of debates between people working in data science and people working in survey methodology, and they are actually telling each other that they are doing it wrong. And I think that both are doing right things, and they should actually work together in solving this problem. So the problem is the following. Sometimes you have a very small area in your data set, and you need to have a classifier which classifies that small area. For instance, when you look at the number of artificial intelligence companies in your country, are look very much like IT companies, and it's really hard to find a model which actually finds that small area, that black swan. So somehow we have to find a way to deal with these very small areas to get the right features. And in my opinion, but that's my opinion, this all has to do with the fact that a lot of data scientists work with found data, which does not cover the complete population. What we actually need to do is use techniques that we already developed for a long time in survey statistics. we have to look at random sampling, stratified random sampling, and within the stratified random sampling, we have to see how we define the strata. And we can just use the background information like we do it always when we are trying to find an optimal stratified random sample. But we could also use clustering features on the input feature space because there's already some inhomogeneity over there, and we have to create some homogeneous groups in that input already. And if we already have that, that could help us a lot with finding the right strata. So another problem that appears then when we have a stratified collection is how we are going to combine it in the model. And we could, for instance, use weights. Some machine learning algorithm let us introduce weights in their models. But what is wrong with it by just defining multiple models for each stratum? So have a stratum and have a model connected to it. So have as many models as we have strata. And some researchers are already doing that when you have hierarchical codes that have to be classified. So if you have to classify it into an hierarchy, then you can, people did some experiments already with it, but having the notion that you have an inhomogeneous data set, an inhomogeneous population, and that you stratify your inhomogeneous population into homogeneous subpopulations and create models for each and every homogeneous subgroup is actually not that far-fetched, but it is not done yet. So, and we are starting up some research in that direction at this moment. So then my last topic is on explainable AI. I'm not going to say that much about it, only that when you look in the internet, when you look it up what explainable AI is, then it is about explaining machine learning algorithms that have to be trained. And you do that by looking at your data. So by doing analysis on your data, finding structures in your data, and at the moment that you know what your data is modeled like, then you are going to create your model. You can actually use stratification, like I mentioned before, doing that, which already explains the algorithm much better. You can do explainable model, and at that moment you say, I don't create just any model. No, I'm going to only use models which have that explainability already in there. For instance, when you use decision trees, you already have that the explanation in there, and you don't have to do anything else. The backside of that is that you are limited to more simple machine learning algorithms. So when you have some complex relationships, you will not it will not be able to detect it. Another strategy is post-modeling explainability, and I'm a visual perception guy working in psychophysics earlier, and this is actually the area which I like very much, doing psychophysics on models that I created. So try to find psychometric curves in machine learning algorithms. See what the proportion positives are when I vary a variable in the input, and see if I can find some relationships there that explain why the model is behaving like it is. All that aside, I think another way of looking at explainable AI, at how we explain algorithms, is also a very good one. And this is this one. For me, validating a model is by understanding it, the algorithm. And when you look at validation of models, you should try to understand the model. And that's also where it went wrong when I started to train machine learning algorithms in 2017. And I tried to create these models. I always had this problem. So a lot of researchers look at the representation and algorithm. And so they look at the input-output relationship of the algorithm. They look at the algorithm itself, precondition, postcondition, everything is okay. So they say the algorithm is doing what it should do. And they also look at the implementation of the algorithm. I'm using a certain library for that, and I know that there are some decisions on how the algorithm should be implemented. But the third part, which is actually the most important one in the view of David Parr, which wrote a book in 1982 on this subject, is what is actually, how does the the model relate to the reality? How does it relate to the physical world it is actually working in? Such a model is working in the real world, and somehow we forget to look how it is working in that real world. We only look at the internal validity of the model, but not the external one. So what is the goal of the algorithm? And how do we meet that goal? Why is it appropriate that we use this algorithm in this way, with these features, with this input? And what is the logic of the strategy that we are following? So these questions are not asked that much, but they are really important. How does the model relate to the reality? And that's actually where I would like to end with a conclusion. So quality of statistics is about relevance, accuracy, accessibility, clarity, coherence, and comparability. And when you look at machine learning algorithms, this means that we have a certain research topic, productivity, annotation, ground truth, explainability, clarity, and quantification versus classification. Yeah, and this is really something we are looking at right now, so that we can move from just methods to statistical methods. Thank you very much.
Thank you very much, Marco, for that interesting talk. So if you got any question, you can, as you prefer, either type here in the chat, and then we're gonna read them out, or you can unmute yourself and ask them as you prefer. So.
Otherwise, I'm going to ask questions.
I've got a question if nobody asks any question.
Sorry, I'm just a bit curious. I'm a student doing MSc in Applied Statistics, and I'm keen to look at, I'm looking forward to maybe doing a project where we'll apply machine learning in my project. Marco, I don't know whether there's any guidance or signposting that you can give me in reference to that. I've not yet decided, but because machine learning or artificial intelligence seems to be like the buzzword now, or the trending thought now, which I'm just keen. But it's not structured yet what I want to do, but I'm just, it's something I'm keen to maybe dive a bit more into it. I don't know if you can guide me.
Yeah, just send me a message when you, I don't know if you will have my email. Well, you can find me on LinkedIn, so
okay.
Quite
all
easy.
Right.
So just ask questions. If you want to know my email address, you can also ask Angelo. So he knows my email address. So if you need any help, just. But I think what a lot of researchers don't do is start with the data itself and how the data relates to the real world. And that's within data science we lost the connection with the real world, and that's the main thing. So as long as you start with defining your problem in the right way, then everything will be okay. Yeah.
Okay. All right. Thank you. I'll definitely connect with you on LinkedIn.
Mm-hmm.
We got a question here. Let's see. It's about the notional machine can never do better than the annotators, imply that machine does not learn beyond the training data. Does semi-supervised learning overcome that problem?
Yeah, actually, semi-supervised learning should overcome the problem a little bit. For the people who don't know what semi-supervised learning is, it's actually a. Oh man, no, I'm stuck in abbreviations. These are things that you do with stuff like factor analysis and stuff like that. So you take a data set and you're going to see how you can reduce the dimensionality of your data, so that you actually get a lower dimensional representation of your data. And actually, one of the semi-supervised learning techniques is actually a neural network where you have an inputs and outputs and a very hidden units, which is much smaller than your input and your output, and it tries to reconstruct the input at the output in that way. So that's it's actually like a principal component analysis. So the thing is that at a certain moment you still have to make the step where you have to find a predictor, and so even with semi-supervised learning, you still have to introduce at a certain moment your annotated data, and that's where it goes wrong. So maybe it finds more structure in your data, but still it doesn't do the whole job. So yeah, maybe you could use the semi-supervised learning techniques for finding strange some oddballs in your data. Mm-hmm. There is another question. I hope I answered the question a little bit understandable. So yeah.
We have another question here. When using machine learning for feature statistics, it's not easy to get higher accuracy, low bias. For example, using random forest and survey data. It has a quite high bias, but in general, random forest can give us high accuracy. So do you have any experience?
And there's another remark on that. Maybe it is because of the misclassification bias in official statistics. Yeah, I think there could be some answer in there. So I think whichever techniques that you are using, your model is as good as your feature space and your outputs. So when you have misclassifications in your output already, then it actually influences the model. If you have features which actually help you in separating the data into subgroups and into classes, but it's not in the data set, it already deteriorates the performance of your model. So even if you have something like a random forest, at the moment that your data is not clean enough, it will actually introduce stuff like this. So I think that the misclassification bias is actually a good source for all these problems. Yeah. Mm-hmm.
If nobody asks a question, I'm going to ask a question about small area estimation. Mm-hmm. So you mentioned at the end, I found it interesting about small areas or clustering, or anyway. Mm-hmm. And small area estimation, we rely very much on the model when we use model-based method, and we are very concerned when all the model assumption fails. And then we try new things all the time, but then we want to provide measure of accuracy, of course, in the very end. Anyway, uncertainty, because we don't want to have a smaller bias because we introduce mean-square error because we introduce a bias. So have you got any experience in I don't know, anything machine learning, or because I saw that people are starting using random forest as a sort of mix effect random forest to produce small area estimation. So have you got any experience, any thought about that?
Yeah, we looked normally so sometimes, most of the time, Speed Dawes is also present at presentations that I give, and he's actually actually has a very nice example there, and it's the classification of AI companies. And what you see there, it's actually that is a very small area. Because of the fact that there are not that many artificial intelligence companies in the complete collection of artificial intelligence companies. And what you see, what happens there is that these models, one of the things you are doing with machine learning algorithms is that you try not to overfit them. That's actually one of the things. That's the art of using machine learning algorithms to find a model that performs well but doesn't overfit, and you have to find that sweet spot in the algorithm. And what you see when you look at the sweet spot of an algorithm that classifies artificial intelligence companies, and it actually overgeneralizes the artificial intelligence companies, and you get a classifier for IT companies out of there. And this is one of the problems you see all the time with all those algorithms. That when you use them well, they try to generalize, and when you do not have that many cases in your training set which describe as your target, that it is really hard to find a model, because at one side you only have a few cases. Compared to the complete realm of all the cases of companies in your country, which is a big difference. It's maybe 1% of your total population, or maybe 1 promile of your total population, and your model is actually overwhelmed with all those features which are presented to it, and it's not able to pick up the real signal. Or you're going to balance it, so 50-50. But then the problem is that you don't find a lot of features which are important, because of the fact that you only have a small subset of your complete population. It's actually a representativity problem. If you only have 1% positive cases, and you are going to balance it with 1% of the rest of the population, you're missing out a lot. So your sampling error will be really large. So at the end, the model will not be able to learn anything, so or maybe overgeneralize. And so yeah, that's the main problem that I try to address there. That it is merely impossible for a model to actually find something in those cases. Yeah, it's.
Thank you very much. I think we've got another question in the chat before probably we should finish soon. But anyway, are there any significant testing procedures for variables in machine learning or explainable AI models?
That's a good question. Well, you can, at a certain moment, you could do some significant testing, and for instance, to see, I think what you mean with the question is, wait a minute, yeah. What I think what you mean with the question is, can you do some significance testing? Could you do some falsification on the model? So could I? Maybe she should try to get to the microphone and explain what he or she means.
Yeah, hi. So I'm sorry for the delay. What I was trying to actually ask was whether, like in statistics, in any statistical model which we take, we do have statistical significance testing. So it's being as simple as regression model. We have beta coefficients, and then we decide whether it has a significant impact on my predictions or not, right?
Yeah.
So I do know that machine learning models do have a very feature importance, all right, which we have, all right. But and that feature importance would vary. In fact, if I would have a lot of various iterations going on of the models, all right. But and statistical significance is robust in terms of in whatever way or how many times I would iterate it till the time we have a random sample, and and it do represents my population, all right. So I was just saying that whether a stride has been made towards seeing out if we know that if ML model is explainable and due to these features or variables are deriving my prediction, till what extent they are significant to derive that, or is just random? I mean, say just a chance.
Oh yeah, that's a very difficult question, and the reason why I think it is very difficult is at the moment that I think about significance testing in this context. When I have a linear regression model and I do significance testing, then I have to fulfill all the assumptions on normality, and if I don't fulfill the assumptions on normality, I'm going to use I'm going to use means in my model to be able to assume that everything is normally distributed. So then I assume that I have IIDs and that I just at the end I get out a normal distribution and I can do my significance testing. And the problem is that a lot of data that is used in machine learning doesn't fulfill this assumption of normality. So I don't know if you could state that the significance tests at the moment that you apply them on machine learning techniques, if you are able to say that that the significance that you find, if it is really true. And yes. Suppose you have a logistic regression model. I like logistic regression models because you can understand them so well about how they function. Suppose I have a logistic regression model. Yes, I can find. I can of course do some significance testing on there. I can say something about the significance of I can say something about the validity of the model at that moment. But the question is if I really can say something about it, because I don't know if my data fulfills all the assumptions. So
okay. Thank you so much.
Yeah.
And also, like, is there any progress done for machine learning testing of variables or stuff like that, or it's majorly depending on the feature importance which we get only?
There are many techniques for it. There are ways where people try to randomize the features and see if the model still does something until picking out features to see which features are really important in the classification. So yeah, there are a lot of techniques where you try to find I would almost say find the significant features in your data set. So yeah. But I wouldn't, and some discussions with my colleagues about, I wouldn't say that that's just taking the features out of the models that as you get them, that is really a good way of dealing with features. Sometimes it's also good to already look in front of what kind of features could be interesting for your research. So,
All right. Thank you so much.
Marcus, I think I missed the question before. There was a question from Ahmad before this one about significant testing. It was a question about imbalance training data set for classification. So can you see? Is just before that? So.
Yeah, it's actually one of the problems me and a student of mine tried to deal with a long time ago. It's the problem that at the moment that you have something like, which I like to call a small area. So just a small amount of positive positive or negative cases, whereas you have the other part is really dominant, that you sometimes actually want to have much more balanced data set, and yeah, all those upsampling techniques, also for creating synthetic data, but also if you are going to resample, so always deliver a problem with your deliver problems in your models, and somehow you have to deal with it, and sometimes I hoped that having such a model that I created, such a ideal observer model, where I just going to estimate the proportion positives in my data set, is going to overcome this problem, because it just is going to use the data as it is, and you don't have to oversample. But at the moment that your minority class is so small that it doesn't actually work at all, I would maybe I would say try to stratify your data set, because then maybe you find some way to divide your data already into a group where you have mainly your positive items, and you could have a much better model, because you're right, creating synthetic data sets, oversampling the minority group just by subsampling the majority group is not going to help you that much. So I also was thinking about ensemble techniques, where you just say, okay, I create an ensemble of models, where I try to create much more balance with a different majority group in it, or part of the majority group in there. But these are still things we have to investigate. But yeah, this is the direction we have to look at. Use stratification, maybe. So maybe stratification is a solution, but also creating different models which have different subsets in the of the majority group.
Okay, I think we are, it's already 3:10, but there is another question. Have you got time to maybe answer that, and then maybe it's going to be the last one?
Yes. We can use random sampling and weighting the models. Meanwhile, machine learning models are known to be black box models because of the formula complexity. How do we apply the weights in the machine learning models in this case? Like when using weighted GLM, we can, so some of these classification algorithms have the ability to introduce weight in there. So, but like I said, it makes, and like you also say, it doesn't make it more transparent. And I think that's like I'm selling my point here, but I think that that stratification should be a solution here. So, so the question is about suppose you have at a certain moment you have weights coupled to your items in your training set. How do you apply it? I think my answer should be, well, some of the machine learning algorithms have the ability to apply weights. But at the other side, you should also look at classification algorithms to see if they can. You should look at stratification to see if because stratification makes sure that you have homogeneous groups. So at the moment that you have homogeneous groups, the weights should be equal within each of the strata. But this is still, this is still something we have to investigate. Yeah. I have really good. These were really good questions. I have to say that they really made me think a lot. So it's actually a lot of material where we could do some research. Yes. Yeah. It's great.
Thank you so much, Marco, again for giving the great talk. So which, as you said, it was different than the previous one I saw. So
yeah.
So-
The field is developing at this moment so fast that at Wednesday I also have to give a presentation for a conference, but that one will also be completely different again because of the fact that this is just an emerging field where a lot of work still has to be done. And we wrote a paper in the Survey Statistician about this. And I think it catches the main topics that we have to answer in the next time. And there is a lot of research to be done, and it's also work we cannot do by our own because the questions are so different from each other that you really need a team working on this. So if someone would like to work on topics like these, just let us see if we can work together at a certain moment.
So thank you very much. Hopefully see you sometime in person again.
That would be great.
Okay. So, and thanks everybody for joining this webinar. Okay. Thank you. Bye bye.